Hey everyone, Morgan here. So we're starting off gases. This is a new lecture outline. It is creatively called Gases. We are on page 1, and I think I'm going to break this up and just do it page by page as we go through. Really challenging for me to have to present these without doing demonstrations, because this is one of those chapters where I'll just be blowing stuff up pretty much every day as we go by. So I'm going to be directing you to a lot of YouTube videos at the end of every page. So please humor me and actually go and watch them as we go through this. So some basic properties of gases. In no real specific order, we know that gases will fill the space available to them. So if I give you a balloon that is spherical and you fill it up with helium, it's going to take the shape of a sphere. But if I give you a balloon that's shaped like Mickey Mouse and you fill it with helium, it's going to spread out in the shape of Mickey Mouse. Okay? The gas particles just fly around in any direction that they just happen to fly around in. Okay? It's not predicted by anything. It's just random molecular motion, and that's what happens. Okay? They can expand and contract to fill whatever space is available to them. That does not mean the molecules or the particles get bigger or get smaller. Particles can't gain weight. It just means that the spaces between them get bigger and smaller. Okay? Gases can easily flow. Okay? Now, stack of paper's a little thick. Let me just pull these out here and get down to one. That'll make it easier. Okay? All right. So, if we are standing in one end of a hallway and we squirt some perfume out of a perfume bottle, an atomizer. Eventually, that perfume is going to make it to the other end of the hallway because gases flow that way. Okay? Gases will expand with temperature. Increase the temperature, and the particles are going to get larger spaces between them. You've probably discovered this on that long, miserable drive out to Las Vegas and have a blowout in one of the tires on the car. Okay? Gases have very low densities. Okay? Blow bubbles at the bottom of a swimming pool. Those bubbles go up. Very strange one, but one I always seem to point out. All colored, O-R-E-D, sorry, all colored gases are toxic. So, if there's a gas that you can see, guaranteed it's going to be toxic. Now, I'd love to tell you that the opposites were also true, that all clear gases, colorless, were not toxic, but we know that's not true, okay? We often talk about carbon monoxide, okay, and how toxic it is. But all gases like bromine, which is a red gas, very toxic. Smog, NO2, which is a brownish red, also quite toxic. Okay, now, a little bit of math that's going to come up over and over and over again is the difference between the direct proportion and the indirect proportion. So, graphically put, if we have A and B being your independent variable, A being your dependent variable, straight line going up like that, A goes up, B going up, that's a direct proportion, that's directly proportional. I apologize to you about the cat that's walking around complaining that she wants her dinner, but it's still a little bit early for dinner. And indirectly proportional, okay, a plot that looks like this. As one gets bigger, the other gets smaller. As A is going up, B is going down. Now, the algebraic equivalent of this is the much more important concept for us. A is equal to K constant times B for something that's directly proportional. And when it's indirectly proportional, A is equal to K times 1 over B, or more likely to be said as K equals A times B. Okay? All right, so we're going to be doing a lot of stuff like this. Now, when we introduce gases, we talk about them in terms of 4 variables, okay, or 4 measurables, as my professor used to call them: pressure, volume, temperature, and amount. Now, let's talk about what they are. Pressure, we'll abbreviate that with a lowercase p, sorry. What is it? It's really the push, okay? And if you think about it, and actually let's use that cat that's wandering around here in the room right now as an example. That cat has a habit of sleeping on my back, and I'll wake up in the morning and it's no big deal. Cat weighs about 14 pounds. Doesn't bother me so much. But when the cat wakes up, stands up, and those 14 pounds suddenly are just on 4 very tiny paws. And that's a lot of what we call pressure. When her mass is spread out over her whole body size on my back, it's not a big deal. But what's on those 4 tiny paws, that's a big deal, okay? That's pressure. Now, the definition of pressure is a force divided by a unit of area. So again, when the cat's area is pretty big, no big deal. But when it's quite small, it's a big deal, okay? And the classic demonstration of this, which I don't think is actually legal in the state of California anymore, is to bring in a bed of nails. And you would actually get teachers who would lay down on this bed of nails and have a student break a cinder block on their chest, on the teacher's chest, okay, with a big sledgehammer, okay, and the teacher would survive, okay, because when you've got something like 5,000 nails in that bed of nails, the force is spread out over a very, very large area, okay. Now, the unit. This is actually a really tricky discussion. The College Board hasn't even truly made up their mind. For the AP Chem exam, atmospheres is used about 50% of the time. Torr is used about 50% of the time. Now for the AP Physics exam, they limit it to kilopascals. However, I've never seen kilopascals used on an AP Chem exam, so this is about the last time you're going to hear me mentioning it, okay? We'll pretty much limit our discussions to atmospheres and torr, okay? Now, I would probably demonstrate in this room, in the classroom, with that big, heavy atmosphere bar, which you probably saw me working with last year. Do a few things along those lines, bring out the vacuum pump, a few demonstrations with it. Volume. Volume, capital V, okay? What is it? It's space. I think we all understand that pretty well, okay? Definitions. It depends upon the shape. We'll probably just say length times width times height, okay? Or, 4/3 pi r cubed for a sphere, etc., okay? The unit's going to be the liter. Or we have a few other versions, milliliter, etc. Okay. On some occasions, they might revert to the cubic centimeter, which is the same as a milliliter, but we never use things like gallons or anything like that. Okay. You might need to know, it's a stretch, that a liter by definition is a cubic decimeter. Decimeter cubed. Okay? But that one's just not a very big deal. All right? You know what a 2-liter soda bottle looks like, maybe even a 1-liter soda bottle. You understand liters. Temperature, capital T. What is it? Well, it's molecular motion. That's what it really is. Okay? The definition is based on the average kinetic energy of the particles that make something up. So bar over something typically means average, so the average kinetic energy. Our only unit is the Kelvin. Okay? That way we don't end up with any negative numbers. All right? I really want to emphasize to you the concept that temperature is molecular motion. Now, demonstrations for volume and temperature are really straightforward and something you can do at home. I just keep a collection of empty soda bottles in the room. I've got a 500 milliliter, a 1 liter, a 2 liter, and a 3 liter soda bottle that I show. Everybody understands volume. For temperature, I take a beaker full of ice water, a beaker full of boiling water, and I put a drop of food coloring in each. You can do that at home. Have a pan of boiling water on the stove. Have a glass of ice water next to it on the counter. Put a drop of food coloring in each and watch. Make sure you're wearing your goggles. You might want to have the younger siblings around just so you can check it out. Okay? They might enjoy seeing that. Amount, lowercase n. What is this? It's counting. It's how many particles are there. How many particles? Okay? The definition is based on moles. Okay? Or 6.022 times 10 to the 23rd. And moles was actually born out of this chapter. Okay? So let's try and understand that. And our unit here is the mole, M-O-L-E. Okay? Now, a few of the things that I would be passing around the room in this chapter would probably be some of the stuffed moles that my wife has made over the years, some of the mole bottles that just show you one mole of different substances. Okay? And we'd probably be getting ready to do some vacuum pump stuff, which we'll talk about on the next page. Okay, so I'm going to end this video here and start the next one. We'll do a different video for each page of the outline. Okay, this is Morgan signing off.